Okay, let's look at this north tower a little more. Here's the top section that comes crashing down, and according to NIST, this crushes the lower section of the building. This is the north tower. It has that antenna on top, all right? Now, the key observation that I made was actually measuring the downward acceleration of the roofline. And we found that it came down at about 2/3 of the acceleration of gravity. It's close to that. Okay. Now, the fact that it's accelerating downward is the key observation. And the conclusion we came to is that this top section of the building exerts a force on the lower section of the building that's less than simply the weight of this by itself. In other words, it was giving more force downward if it were just simply sitting there than in motion. And that seems very counterintuitive to people. But let's go through and just clarify how that comes about, okay? So we do what's called a free body diagram when we're analyzing things in physics. So this is just the top section of the building. And let's look at the forces at work on the top section. We have gravity downward, which is, since this is coming at, right, this is the weight of the building, which is its mass. This has some amount of mass times the acceleration of gravity. There's also an upward force, which we'll call F. This is the resistive force. All the steel and all here is pushing upward, preventing it from just free falling. And so if I get what is the net force, it's the downward force minus the upward force. So it's mg here minus that. Okay, this is the net force, and that's equal, this is Newton's second law, says the net force is equal to the mass times its acceleration. But we know what the acceleration is. It's 2/3 the acceleration of gravity. So let's rewrite this. mg minus F is equal to m times 2/3 of g. Now, if I do a little fancy algebra, I'm going to move the force over there and this thing over here. I have the force, this is the resistive force now, is equal to m times, here's the g on this side, and I'm going to subtract this one, so it's minus 2/3 of g. So if I have something minus 2/3 of it, I have 1/3 of it left. So I have 1/3 of mg. So the resistive force is roughly 1/3, and this, as you recall, is the weight of this top section. So the net force of upward force pushing on this block is 1/3 of its weight. And that turns around because of Newton's third law. If the upward force is 1/3 of this thing's weight, the downward force is 1/3 of this thing's weight. So this is pushing down less than if it were simply sitting there. Now, how can that be? In normal experience, if you have something moving, you would think you would hit something harder than if it were simply sitting there. The problem is, as it hits, it would normally decelerate. So if you hit your fist on the table's going to slow your fist down. Okay? But here we have, this thing is coming down, and it doesn't slow down. It accelerates right through the interaction. It keeps picking up speed, as though there's nothing there. And that's the key idea. There's nothing here, because this has already been blown out of the way by something else. So this observation, the fact that this can continue to accelerate through the interaction, tells us that the tower down here, the lower section of the building, has been pre-pulverized to allow this to simply fall through it, accelerating the whole way. And that's the key. So no, this can't crush the bottom section of the building with less force than its own weight. It's falling through a pulverized mass of material. Okay, there's one other comment I'd like to make about this North Tower. There's the North Tower. And I want to credit Tony Zambodi. He's a mechanical engineer from back east. And it was a conversation with him that helped me clarify my own thinking about this. One of the problems with thinking of this as a block crushing this other block is you think of two solid objects hitting each other and somehow demolishing each other in the middle. In fact, it's a lot of hollow space, and what we have are these columns that run the full length of the building. There are 47 of these interior columns, very heavily cross-braced. Okay, and then we have all these perimeter columns, which are not just for show. Those are very solid supporting members as well. But according to the NIST theory, this broke somehow here, and then as they come together, this somehow crushed down the lower section of the building. In order for it to crush, these columns would have to hit head-on with these columns. It's sort of like hitting directly in line. But in fact, there's more of a tendency for them to sort of spear past each other like this. And so how would this actually crush this part of the building? This has been used to argue on both sides of this. But what if they missed? How would, could this top section of the building then just plow through and tear apart the core structure, for instance, of the bottom section? And what Tony pointed out, which is sort of obvious once he mentioned it, is that as these things come together, it's going to tear up the cross bracing of both the top section and the bottom section of the building equally. And so by the time this top section has come down its own distance into the lower section of the building, if this is what's happening, then it's going to have basically shredded this whole interior structure. We're not going to have a block left at all. We're going to have a bunch of loose material. And with all this stuff coming out the side, there's nothing here to crush the bottom section of the building. And yet we see this crush process goes all the way to the ground. So I think what we can conclude is it's not a crushing process at all. There's something else happening. This little block up here is not capable of totally demolishing all of this structure below, whether we think of it as solid blocks or whether we think of it in terms of these cross-braced columns here.